Today, just a second, I start the recording. But today, let's talk more about the endogeneity problem. What is this? How can we detect this problem? And what the problem really is. So, if you remember, one of the main assumptions among ordinal least squares method assumptions is that our error terms or our stochastic term or our disturbance term, this is the same definitions of the one thing. So the error term in the linear regression model must be uncorrelated with the explanatory variables. Or it's better to say even error terms and our axis or our independent variables should be independent. And sometimes, unfortunately, correlation or let's say any relationship could exist between the error term and between the independent variables. And this correlation or relationship leads to biased and inconsistent estimators. So our result will be really very bad. And of course, there exist different reasons why these error terms could be simultaneously correlated with one or more than one independent variables. So today we discuss all these reasons, and they are really very, very important. So it's really very important that you will understand this topic very clearly. If you remember, we discussed through the first lecture that in most researches or in economics or in business or when we implement different policies, our main goal to find how one or let's say several variables affect our dependent variable. But of course, first of all, we want to understand not only this effect, yes, this quantitative effect, but of course we want to understand the causal relationship. So we want to understand the causal effect of one variable on the other variable. And because of this, when we start our discussion about the multiple regression models, we used the ceteris paribus interpretation. You remember, that ceteris paribus means holding all other factors fixed, or it means that other factors being equal. And this phrase plays a real, very important role in causal analysis. For example, if we want to understand the relationship in consumer demand, we're interested in knowing the effect of changing the price of some good or some service on its quantity demanded. And of course, we want to find this relationship while we're holding all other factors, such as income, such as prices, such as maybe other goods from the other competitors. And we want to fix all these factors and find how only one factor affects our main interest here, to find the relationship between our main factor and the demand. And if other factors are not held fixed, then you cannot find the answer on your research question, and then you cannot find the causal effect of price change on quantity demanded. And the key question here is have enough other factors being held fixed to make a case of such causal relationship. So you need to understand clearly that when you make empirical research and, for example, you run ordinal least squares regression, it doesn't mean that you find the causal relationship. Because how you construct your model, which factors you include in this model, which theory you use when you explain the relationship between the variables, it's your choice. And ordinal least squares regression itself doesn't mean that you identify the causal relationship between the dependent variable and the variable of your interest. It doesn't mean. But of course, in regression analysis, we try to estimate the average value, the average effect of one factor on the basis of the fixed values of other variables. If you hold all the assumptions of ordinal least squares method, in this case, you can find this relationship and your results will be reliable, yeah? But this could be only in the case when your coefficients will be blue, best linear unbiased estimators. And if your model based on the theoretical background will be a right model, yeah, a right theoretical model. And one of the main assumptions to say something about the relationship, yeah, you remember that that your error terms should be independent of the explanatory variables. So there should not exist any correlation between the disturbance term and your X factors. Okay, so you should remember that before any equation can be estimated, it must be completely specified. This is the first step. I hope that in your team projects, you have already find the proper specification of your models and you start to find the answer on your research question through the regression analysis. But you should remember, and please check yourself, that first of all, when you specify your models, the first step, you need to read the theory, yeah? After this, you need to find the correct independent variables as well as, of course, dependent variable. You need to construct the correct functional form, so you need to use the right specification of your model. And of course, you need to find the correct form of stochastic error term. And these three parts are really very important if you want to find the answer on your research question through the ordinal least squares method, as well as, I should say, any method that you used in the regression analysis, in the econometrics analysis. What does it mean, model specification? And the very close question, what is misspecification? Because, of course, we want to avoid the misspecification errors when we start our empirical research. So misspecification we can understand in two ways. And the first question that we can ask, what happens when a relevant variable is excluded from the model? This is the first main question. And I think that you know the answer on this question because you remember what is omitted variable bias is. But the second question, of course, we can exclude some relevant variables from our models, but this could be exist the opposite situation. For example, we so scared of misspecification errors, and we want to include in our model all the variables that we can include. So the next question, what happens when an irrelevant variable is included in the models, in our model? So should we assume that even in this case we will obtain some errors, or our result will be not reliable? Okay, so let's start with the discussion of these two main questions. But before this, you should again remember, that not all, but most of the problems arise when you violate some assumptions that connected with the error terms. Previous time we discussed the heteroscedasticity problem. You remember, that this means that the variance of our error term will not be constant across the explanatory variables, across the different group of populations. And we learned how can we fix this problem, how can we change our standard errors, and how can we use the robust standard errors, or in other words, robust to heteroscedasticity standard errors. And in this case, this is one of the approach how can we deal with the heteroscedasticity problem. But this is a relatively minor one problem. So all our further discussion in this moment will be about the much serious problem and correlation between the error term and the correlation between the explanatory variables. And we call this situation when one explanatory variable, or let's say some group of explanatory variables, are correlated with the error term. We call these variables as endogenous variables. So, for example, omitting a key explanatory variable can cause correlation between the error and some of the explanatory variables. And of course, this situation leads to bias and inconsistency in all of the ordinary least squares estimators in general. And this is an example. And in the special case, the omitted variable is a function of the explanatory variable in the model. So in this case, the model suffers from functional form specification. This could be the second main reason why indigeneity problem arises in our analysis. So let's start with the first point, with the choosing. How can we choose independent variables? So if you don't include one of the relevant independent variable when you specify an equation, you obtain omitted variable bias. We discussed this. If you want to find more details about why this will be a problem, please check our 6th lecture. We discuss in details with a lot of examples why this will be a problem. And I just want to know that the best indicator of an omitted relevant variable, first of all, of course, this is the theoretical background of the model that you use. No one test, there's no among existing tests can exactly say that you have the admitted variable bias problem. Because of this, first of all, please think about the theory. Okay? And the second point, this is irrelevant variables. So when you include irrelevant variables in your model, so could you assume that even in this case, you will face some problems, or maybe even your model will not be, so the results from your model will not be reliable. Let's say that we specify some model with 3 explanatory variables, and this model satisfies unbiasedness and of course consistency assumptions, but the last variable here, x3, has no any effect on your dependent variable after you control for x1 and x2. And in other words, we can say that the coefficient of that associated with the x3 variable will equals something around 0. So if you want to explain this idea in mathematical language, yeah, we can use the expected value, and we can write this in this notation, that the expected value of your dependent variable that depends on x1, x2, x3 can be just equals this equation, and the expected value of beta 3 coefficient just equals 0. And of course, maybe even beta 3 coefficient itself will never be exactly 0, but we should say that average value across all random samples from our general population will be 0. Yeah. So what does it mean? Including one or more irrelevant variables, or in other words, we call this situation that we overspecify the model. So when we don't include relevant variables, we underspecify the model, but when we include irrelevant variables, we overspecify the model. In general, the good news that your coefficients in this example, beta 1 and beta 2, still could be unbiased and consistent. But the problem is that you increase the variance of the ordinal least squares estimators of these coefficients, and your estimated parameters could be generally inefficient because of this large, or let's say larger variance, if we compare with the model when you not include this irrelevant variable x3. Okay, so this is the main problem. And so when you think that it's better to include more variables in your model than not include them, if you're so scared about the admitted variable bias, this is also not a good decision in this way. So let's take a look at the example. This is rather simple example. We want to study the impact of beer taxes on traffic fatalities. So our main assumption that a higher tax on beer will reduce alcohol consumption. And so drunk driving resulting in fewer traffic fatalities. This is the chain of our logic. Yeah? This is the chain of our idea. So as the dependent variable, we of course want to measure some fatality rates, for example, yeah, or the cases of fatalities for some, let's say, 100 of people, for 1,000 people, let's say. And the main interest here is the independent or explanatory variable tax. Yeah. This means the B taxes. And also you want to include some control variables, of course, such as total miles, such as percentage of state population that is male, and also you can include some other variables such as percentage of population between some specific age groups and so on. Doesn't matter. In this case, it doesn't matter, because we need to discuss what will be if you after this step, for example, you think that it's not enough, yeah, and you want to include the variable of beer consumption literally and directly in this equation. So, for example, you use, of course, the same dependent and all the independent variables, what you add beer consumption in the first equation. So really it will be very strange, yeah? Because if you remember the main interpretation of our model in multiple regression model, you interpret this through the ceteris paribus effect. So in other words, you want to find how the change in tax rates affect the decrease or increase in the fatalities rates, holding beer consumption fixed and all other factors. Yeah. So what does it mean really? How would beer taxes affect traffic fatalities if we hold beer consumption fixed? So we understand that beta 1 here measures the difference in fatalities due to a 1% point increase in tax. And in this case, we should not be controlling for differences in beer consumptions unless we want to test for some sort of, let's say, very strange and maybe indirect effect of beer taxes. The main idea of this example, yes, that in some cases, it makes no sense to hold some factors fixed precisely, yeah, because they should be allowed to change when a policy variable changes. And there is no any logic to include beer consumptions here directly, yeah, and to find the effect of beer consumption precisely if our main question is how tax rates influence the fatalities rates. Okay, so remember about this when you think which variables you need to include in your model. So misspecification means that you include irrelevant variables in your model or in your models, even if the coefficient of this irrelevant variable will typically, let's say, have zero effect, yeah, in your sample, yeah. But it typically increases the variance of the estimators for other coefficients in your model. So including many variables in your research is not a good strategy. Please remember about this, especially if you work with these small samples. But from the other side, misspecification also means that you exclude some important variables that correlated with the other axes in your model, and including too few variables had the danger of biased estimates and omitted variable bias problem. That is really very important and very serious problem in whole your research. And this, so maybe you have a question. So if we have so huge problems with the misspecification errors. What should we do? And maybe we have some guide how to select the set of regressions. Of course, we don't have some unique rules how to do this, and there is no unique guide that I can show you and say, if you follow this, let's say 10 or 15 steps, you will always get excellent results, and you will always find the reliable and good and best linear unbiased estimates. Unfortunately, no. But of course, you can use some criteria that can help you to specify your model. And first criteria, many students, I don't know why, but they don't like when we start talking about the theory, but unfortunately, the first criteria is the theory. The models that you use should be based, of course, on the proper theory. And you should ask yourself if the variables placed in the equation are unambiguous and theoretically sound. So you should find potentially relevant variables that you can use from economic theory, from, or let's say business theory, or from management theory. You should read relevant articles, textbooks, and maybe some other relevant and reliable sources. This is the first answer, and this is the first criteria. The second one, of course, you can take a look at the t-test, and you know, yeah, how to do this. We have learned to use proper statistic since our first lectures, and even since from your statistic course. So the question is the variables estimated coefficient significant in the expected direction? So first of all, before you run any regression analysis, you should make some hypothesis about the significance, about the direction, about the science of your coefficients that you will obtain after you run the regressions. And then, of course, you should check if your assumptions holds, if your hypothesis, if you obtain the same result that you assume during the first steps in your analysis, okay? So, a next criteria, you should take a look at the adjusted R-squares. And does the overall fit of your model, of your equation, and if we talk about the multiple regression, of course, you should use adjusted R-squared, not the general R-squared indicator. So does the overall fit of your model improves when the variable is added to the equation? And the last one, main criteria, is that do other variables coefficients change significantly when the variable is added to the equation? So when a typical omitted relevant variable is included, it will increase your adjusted R-squared, and it will be a kind of signal for you that you're on the right way in your research. And for example, if you include an irrelevant variable in your model, it will reduce adjusted R-squared, and also you can find that insignificant t-statistic, t-score, and also the irrelevant variable with the high chance will have a very little, very small impact on the others variables that you have in your model. So all of these criteria could be a kind of signal for you when you work with the models, when you construct and when you think about the specification of your model. But of course, the main point here is the first one. Theory is our basis. And also you should remember that whenever our 4 specification criteria disagree, the researchers and the econometrician must use very careful judgment and should not rely on a single criteria, like just adjusted R-square, yeah, let's say, or just the significance of your t-statistic in the regression output. So there is no amount of statistical evidence should make a theoretical necessity into an irrelevant variable. So please remember for the whole your life, it's no, this is maybe not right phrase, but at least till the end of our course, or it's better at least to the end of your econometrics store course, that you can't just exclude, or let's say drop, irrelevant variables from your model if you see that this variables is insignificant. It will be a very bad situation and very bad mistake, okay? Remember about this, because this is very common mistake among the students, that they check the regression output, they see that some coefficient associated with the variables are insignificant, and they just decide to drop these variables from the models, even if the theory states that you must include these models in your these variables in your models. Okay, this is a very rude mistake. Okay, next topic. So the issue of how best to choose specification from among alternative possibilities, of course, is difficult, especially if you don't have any experience in the empirical research. So use some common recommendations. Remember about the theory, yeah? Because from the theory you can find relative variables, first of all. Also, you can find relative and functional forms, and so on. And also, don't test different combinations of variables until they find the result that appear to statistically support the point you want to make. So we understand that you can manipulate with your data, you can manipulate with the models, with the model specification, you can even manipulate with the variables. But generally speaking, we can always see that you did some manipulations. And again, it will be very bad if, for example, we noticed such kind of manipulations during your project, or let's say thesis defense, okay, because your mark will significantly decrease after this, your final grade. So next point, that most of the work of specifying a model should be done, of course, before you attempt to estimate the equation. So first of all, you need to write down the theoretical model, an econometric model, and only after this you should start to work with the data in Stata, for example, and run your regression analysis. Of course, after you run some regression analysis, you can correct your models. You, for example, can run different tests, and after this test you can correct and add maybe other variables, or you can add some, you can choose the functional forms, but anyway, the basic model should be constructed and should be written down before you start working with your analysis. And also, please remember that, and this will be a very good for your research project when you run not only one model, yeah, during your regression analysis, but you can use sensitivity analysis. What does it mean? Sensitivity analysis consists of running a number of alternative specifications to determine whether your particular research will be robust. So you answer the question how sensitive a potential best equation that you choose to change is specification, because the true specification is not known, yeah, let's say. So the purpose of your sensitivity analysis is to gain, let's say, confidence that your result is significant if you change, let's say, if you use alternative specification of your model, alternative functional form, or if you choose alternative variables, or you add more controls, or you choose the subset of your sample. So this is very good when you run sensitivity analysis. So in this case, you can add all the additional models with all their sensitivity results in a footnote, or it's better to include them in the appendix as alternative specification. And this will be a real good proof that your result is really reliable. Please remember about this. Don't stop only on the one model in your research and in your regression analysis. Try different combination, try different sum samples, try to add alternative independent variables. Will your result will be almost the same? Will you gain the same conclusion if you change something in your models, okay? So now let's talk about the functional form specification. You should remember that multiple regression model, of course, if we talk about the functional form specification, this discussion is more about the multiple regression models when we have different variables. Multiple regression model in many cases could suffer from functional form specification. It means that you don't properly account for some relationship between the dependent and the observed explanatory variables. For example, omitted variable bias, yeah, omitting function of independent variables is only one way that how model can suffer from a specification functional form. But of course, there exist some other problems of functional form specification. For example, you want to find the effect of education on the level of wage. And the true model will be logarithm of wage as the dependent variable. And you include education, experience, and the quadratic form of the experience in your model. But let's imagine that for some reasons you have decided not to include logarithm of wage, but you include just wage in levels. So this variable wage will be in levels of the dependent variable. And again, in this case, you will obtain biased and inconsistent estimators. Another example that, for example, let's say that you omit the squared experience term from this equation. And again, you will face the problem of functional formula specification. And again, your result could be biased and inconsistent. But we discussed with you the most popular device in econometrics for allowing nonlinear relationships between the variables. In many cases, using logarithms of certain variables and adding quadratics terms in the models are sufficient for detecting many important nonlinear relationships in your equations, in your models. So if we talk about the economics, if we talk about the business, if we talk about the management areas, these two devices will be enough in most cases. But also, of course, we can use some variations and extensions on functional form that often arise in applied work. So we discussed a lot during the seminars, or during the only one seminar, but also we used the quadratic terms now a lot in our models. And I hope that you remember how to implement the models with the quadratics. And I hope that you remember when you interpret the coefficient that associated with the squared terms of some models. First of all, you need to remember about the vertex. So you need to remember about the turnaround point, how to find this point. And if you don't remember, please check this formula, check the information and the formulas from the slide. And also you should remember that the slope, the difference in the interpretation, that the slope of the relationship between x and between the dependent variable now depends on the level of x. And because of this, when you interpret the relationship through such kind of variables with the quadratic terms, you always need to plug in the specific values of x in your, not in your, in this formula. Yeah, we have practiced how to do this during the seminar. So if you don't remember, please check seminar notes and please check this slide. And also we discussed how the model with quadratic terms look like. Not the models, how the relationship is better to say. So it looks like U-shape relationship or inverted U-shape relationship. And also, of course, you should remember that in many cases, it will be very useful to include the quadratic term in your model, especially you remember the case when we work with the dependence of salary on age. Yeah, you remember that till the picture will looks like this. For example, if we include h squared in your model, so till the sum point, till the sum age, you can assume that your wage will increase, and after sum age, you can assume that the wage will decrease. Okay, and also when you work, for example, with the model of cost production, also it will be relative to include again the quadratic term in this case. And also you should remember that we discussed previous time the variables that named the interaction terms. Yeah, you should remember that also we can include in our model the product of two variables, for example, dummy and continuous variables. We discussed this in the previous lecture, that, for example, you can include dummy and continuous variables when you assume that the relationship between the continuous variable and the dependent variable depends on the group of sample. Yeah, for example, for male and for female, the relationship will be different. And we discussed how to interpret such kind of variables, and also we discussed how we can implement such kind of variables in our models. But please remember about this also. And now let's talk about the additional specification criteria. Let's continue our discussion. So, of course, we have looked at 4 criteria that can help you to choose the independent variables. This is, again, let's recall again, economic theory, adjusted R-squared, t-test of your coefficient of your variables, and of course, possible bias in the coefficient when you include or exclude some variables. This also could be a good signal for you. But also, sometimes all these criteria don't provide enough information. For example, you have 2 different specifications that both of these specifications have excellent theoretical confirmation, and you can choose which model will be the better, let's say the best, not the best, but which model will be more reliable in the context of your research. Of course, you can run different models. Please remember about the sensitivity analysis, but also you can use additional, often, let's say, more formal specification criteria to provide some comparisons, because anyway, even if you run the sensitivity analysis, you need to compare your models. So you need to use some indicators to do the conclusion. Yeah. So you need to take a look at some statistics, or you need to take a look at some indicators and say that, for example, this will be your main model, and other you just use as the models from the sensitivity analysis. And you should always remember anyway that no test, no matter how sophisticated and how good this test will be, no one test can prove that a particular specification is the true one. So now we move to some tests, but please remember about this top point. This is a real very important point, because students very often want to find some unique test and find based all the results on the from their model, but they choose the let's say best model based on some test. You can't do this, and the use of specification criteria must be tempered with a healthy dose of economic theory, first of all, and also common sense, of course. So please don't rely on any tests. You can use them only as the additional support for your conclusions, but not only as the unique, let's say, unique and right rule. So now we are going to describe some popular, let's say, specification criteria. And let's start with the Ramsey regression specification error test, or reset test, or shortly Ramsey test. For example, you want to test whether individual wages depend on the experience. And you want to test the significance of squared experience. So should it, if, for example, you don't find the proper theoretical model, but you have some assumptions due to your common sense and due to the logic that, of course, experience could be included in this model, not in the linear form, but also in the square term. And for such kind of situations, Ramsey has suggested a test based upon the idea that under the null hypothesis, non-linear functions should not help in explaining your dependent variable. So the easy intuition behind this test is that Ramsey have added some polynomials, maybe not only squared, but let's say in general some polynomials, in their ordinal least squares fitted values to original equation, to your original model, to find some general kinds of functional form misspecification. Or it's better to say, for example, should we add some squared or some other polynomials in your original model, in your true population model, let's say. And if the proxies can improve the overall fit of the original equation, then you have some evidence that there is some sort of specification error in your equation. And let's take a look at the steps of this test. They are really very, very easy. So first of all, you just need to run your original model using ordinal least squares method. After this, you should obtain the fitted values from this model you had, and you create some polynomials from these fitted values. And in the second step, you regress the same dependent variable on the same axis, but also on the polynomials of the fitted values, and also plus some error term. So we call this as auxiliary regression model, and maybe it looks a little bit confused for you. So why from the left side here is y, and again on the right side here again fitted values from this y, from this dependent variable. But this is, let's say, this is technical node. So this just auxiliary regression that we want to use to compute a test statistic only, and we will not be interested in the estimates of these parameters really, yeah. We only want to test whether has missed some important non-linear variables in our model. And after this, after the second step, we jointly test the coefficient of these polynomials equals 0. For this purpose, we can use joint test and F statistic. You remember how we can run test about the joint significance of some variables. and why we should use here f-test. So, and that's all, yeah. But how can you do this in Stata? In Stata, you can find the command stat of test. This is, of course, post-estimation command. So first of all, you need to run your regression, and only after this you can run the Ramsey specification error test. But also, in most cases, you even don't need to include the cubed terms in your regression analysis, or even higher polynomials in your regression analysis. In most cases, it will be enough to include only the square terms. And so you can find in Stata the simpler test is provided by link test command, and this test include not all the polynomials that you want to include, yeah, but only include the square terms, and that's all. And you should remember, after you run the Ramsey test, and after you take a look at the statistic and at the p-value that's associated with this statistic, while the Ramsey test is really very easy to use, you should use, not you should, you must use this test as only the signal when a major specification error might exist. This only a signal, because sometimes, of course, as any other tests, Ramsey test could be very sensitive if you have the, let's say, mixed variable bias, and Ramsey test could reject the null hypothesis of the omission of relevant variable from the model, rather than just a function of form misspecification. So the inclusion of an additional variable may capture the nonlinearities that indicated by the test. And this is only one reason why and how can you use this test, okay? Only for detection the nonlinearities. So, for example, the square terms or cube terms in your model, in your original model. And I want to warn you that please don't make a common mistake. Common mistake, I mean, for students. Some students in the, for example, reports run this test and write the conclusion that there is no omitted variable bias problem and there is no endogeneity problem after this test. You can't write such kind of conclusion after this test. Yeah, I want to repeat again that this test could find only nonlinearities, and to be exactly only should you include some squared or should you include some polynomials in your model. That's all. And so, general conclusion that this test often ends up being more useful in supporting, only in the supporting researchers' conclusion, researchers' contention that a given specification has no major specification errors or nonlinear variables, then you can find exactly what the error is, okay? But also this is a good test that you can use. Next, before we discussed other tests in general, I want to discuss with you some specific definition. And I think that you will face with nested and non-nested models in the further topics of your course. But let's discuss now what does it mean. So you see here two models, model A and model B. And when you carrying out specification testing, it's very useful to distinguish between nested and non-nested models. So you can notice here that these two models looks pretty similar. Yeah, they have the same dependent variable, and also they have the same independent variables, but the model B here is shorter and not include variable x3, x4, and x5. So in this case, we can say that model B is nested in model E because it's just a special case of model A. And if we estimate model A and test the hypothesis that all these coefficients jointly equal 0, and we don't reject this hypothesis, we can just reduce model A to model B if all these coefficients will be insignificant. Yeah, so this means model B is nested in model A, or these two models are nested models. Let's compare with the model C. Let's find the difference. So in model C, you can see again the same dependent variable and even the same independent variables, but these independent variables in the different functional forms. We plug here x1 and x2 after we use the logarithm form of x1 and x2. So we can say that model C is non-nested in model A. And because of this, we can say that model C, of course, is not a special case of model A. So this is the difference between these two definitions. Now, in general, you can find that there exist different tests. But if we want to continue our discussion about specification testing, some of the tests could be useful only for nested models, and some of the tests could be useful not only for non-nested models. So, for example, when you have two models and both models involve the same dependent variable, we can choose between two of these models based on some goodness of fit criteria. The basic ones is R squared or adjusted R squared for multiple regression models, yeah? You know them, but also we can use some other criteria. For example, we can use Akaike's information criterion and bias information criterion and J-test. So now let's discuss the criteria that we can use not only for nested, but only for non-nested models. It means that we have different explanatory variables and different forms of the same explanatory variables. So let's start with the J-test. Let's take a look at two models again, model C and model D. You can notice that dependent variable is the same in both equations, but independent variables are different. So how can we compare which model is, let's say, better, yeah? Model C or model D, when we want to interpret our results and choose the main model. These models are non-nested models, and we can run the J-test. So if you want to run J-test, the null hypothesis here Okay, let's start with the first step and then discuss the null hypothesis. So first of all, let's start with the model D. Of course, you can choose any other order, but let's start with the second one. Let's estimate model D and obtain the estimated values of your dependent variable. In the next step, you add the predicted value in step 1 as an additional regressor to model C. And now your model C looks like this. So the same variables, x1, x2 from your original variable or from your original model, but also you include here the fitted values from the model D. And the null hypothesis here that this coefficient equals 0. So if you not reject this hypothesis, model C, you can use t-test for this purpose, yeah? If the null hypothesis is not rejected, we cannot reject model C if we choose between these two models at the true model. And also you can, after this, you can reverse the rows of hypothesis. Now you do the same steps, but first you estimate model C, obtain the estimate values of your the same dependent variable, yeah, and include these fitted values in the model D. So the same steps, and again you can use test statistic, and now you check the hypothesis that beta 3 equals 0. And again, if you not reject this null hypothesis, it means that model D, it's better to choose model D over model C. So the idea behind this test is really very simple. So the idea that in the first case, when you follow the first from the first 3 point here, it means that the first model contains the correct set of regressors. Then including the fitted values from your second model into the set of regressors should provide no significant improvement. And because of this, your null hypothesis here is that the coefficient associated with the fitted values from the second model equals 0. So it means that included more regressors from the model D will not improve the information about the dependence or about the relationship between the x variable, some factor, yeah, and your dependent variable will not significantly improve. Okay, but you can notice that J-test could be very easy and good test, but of course, if you again trace the order of these steps, you can notice here that both of the models test independently. And because of this, of course, J-test can have some problems. And the first problems, of course, you couldn't find a clear winner between these two models, because both models could be rejected. This is a bad situation. Or, for example, neither model could be rejected. So if neither model could be rejected, it's not so bad. If both models could be rejected, yeah. Because in this case, you can find other you can use, for example, adjusted R-square, some information criteria to choose which model will be better. But anyway, if you reject both models at the same time simultaneously, it means that you need more work to find maybe some other model that will better describe your reweightancy. But anyway, please remember that no one test can say which model is better. Yeah, it's just a signal. And also, when you use t-statistic, because you can notice that all this test based on the t-statistic, when you choose t-statistic to test the significance of the estimated dependent variable, you remember, yeah, that t-statistic should follow approximately normal distribution or normal distribution asymptotically. But it's true when we use a large sample. But when you work with a small sample or relatively small sample, J-test may not be very powerful because in small samples, the samples tends to reject the true hypothesis or model more frequently than in O2 because of t-statistic, because t-statistic is very sensitive to the normal distribution, yeah? So again, the final idea, yes, you can use this test, but no one test can confirm that which model will be correct and which model will be better. And also, let's discuss more indicators. Let's name this as indicators, first of all, that can help you to choose between the models. If you have, for example, if you construct and run different functional forms, if you run different models with different explanatory variables. In this case, except the J-test, you can take a look at the information criteria. And we have two information criteria, Akaike's information criterion and Schwarz-Bison information criterion. But you can use just abbreviation AIC and BIC. You can notice that this is not a real test because both of these criteria are based on the adjusting residual sum of squares. You can see residual sum of squares here. And they just involve the residual sum of squares to create some kind, let's say, of index that penalize by the degrees of freedom. So you can use AIC and BIC as methods of comparing alternative specification, where you can find that you adjust residual sum of squares by the number of variables, yeah, and the total number of observations, or let's say sample size here. And this criteria can be used when you try to decide if you improve, let's say if you improved fit cost by an additional variable is worth the degrees of freedom and increased complexity caused by this addition in your model. Because every time you should remember, when you add more variables in your model, in this case, you decrease the degrees of freedom in your model. And such decretion could be very arguable, yeah. And models with smallest AIC and BIC criteria are typically preferred. So if you see, if you cannot choose which model is better based on theoretical background, based on some other indicators, also you can take a look at AAC and BAC, and they can help you. And you should choose the model with the smallest values of AAC and BAC. And also, let's discuss some problems, that could arise when you use such kind of criteria, because of course, both criteria tend to penalize the addition of another explanatory variable more than just adjusted R squared does, because you can find that the formula looks very different and they penalize more the residual sum of squares, just ordinary adjusted R squared. And also, if you compare both formulas, you can find that even BIC implements larger penalty than AIC. So in general case, you can both add these criteria in your output of regression. So for example, you know how to use the stock command here when you combine all the regression results in one table, a stock command. So in this stock command, you can also present the information about the number of observations in your models. Also, you can present the information about adjusted R squared, and also you can add among these indicators AAC and BAC criterion together. So you can find in Stata the special option how to add them in your regression output through the stock command. And you should remember that BAC can be shown to be consistent in the sense that it will select the true model provided the true model is among the set of being considered, but in small samples, AAC can work better than in big samples, than BAC, I mean. And also, the difference between these criteria with the Ramsey test is that Ramsey test is useful as general test of the existence of some specification error. So this is test for the functional form. This is test for the non-linear terms. And BIC and AIC has a little bit different task and a different goal. So you can use these criteria when you want to compare and choose the more general form of specification, not only some non-linearities, of course, but also when you take a look in general, in common sense, on models with different variables, not in the linear term, okay? So let's stop here today, because next time let's summarize all this discussion, and this sum up will be very important for you, for your research projects, as well as for your general empirical research behind our course. So, but let's stop here now and let's discuss your questions.